going to start. It's going to be mostly I've coded conversation, live coded talk. But I'm going to start by slowly introducing the topic and myself. And we're going to run a bit into the next break because the schedule is a little bit run over now. So we're going to talk about native code, accessing native code from Java using a tool called jextract. First of all, my name is Anna. I'm working as an advocate in the Java team at Oracle. You can find me on social media, the handles that are listed in the slide. And I enjoy working with Java security, also with native libraries and jextract, hence the presentation of today. And I'm looking forward to answering more questions about accessing native libraries from Java using foreign function and memory API, jextract, and more. But without further ado, what problem do we try to solve today in this talk? Well, the problem that this talk aims to solve is those cases that when you're developing Java applications, you have certain use cases when you require access to libraries and third-party memory that is written in other programming languages. And that can happen. And it's not just one programming language in this world. And while there are many great Java libraries out there, there are many other great native libraries. And these libraries should not be written in Java. So why not take advantage of that while we are in Java, having a Java client, but not rewrite everything in Java? So just to give you some examples of what these native libraries can be, let's start with our own computers. On our own computers, we have system APIs, we have USB. These are native libraries that we can access through different ways from Java as well. We're going to see with what we're going to replace that question mark. Then, of course, there are great libraries written with native libraries written in C, for example, that are purposely for machine learning, like Onyx, Runtime, like Tensorflow, and we would probably want to use those as well in Java nicely. How about of CPU computing, like running Java on the GPU? That'd be cool, but not learning all about CUDA and OpenGL and write code in CUDA and OpenGL. How about graphics processing? Wouldn't it be cool to use OpenGL in Java or access OpenGL from Java? And many. So what could we put there in that question mark? And the answer to what you're going to put there in the question mark is FFM bindings. What FFM stands for is foreign function and memory bindings. So these are Java bindings that facilitate interaction between the JVM and the foreign, the non-Java APIs, those native libraries that are available in different forms that as we discussed earlier. So this API for foreign function and memory API for accessing non-Java libraries has become a final feature in JDK 22. So it's final feature in the JDK starting JDK 22. And this brand new API is great for allocating and accessing of memory heap memory, and makes it even more, this access more efficient and much more safe. This API also overcomes some of the issues that, or some of the limitations that were typically had before with the byte buffer API by providing a new programming model that is more centered on the idea that you're programming safe and timely with native memory while being on JVM. And one of the problems that, using the old GNI API was actually the safety and not reaching to dead ends. And that was my mainly problem of having timely deallocation and managing deallocation. So this brings me to the second subject, is that FFM API replaces the GNI with this new low-level API that is much more descriptive and allows us to link into the native functions using method handles. So what FFM bindings mean from Java perspective, from Java API perspective, is working with memory layouts, function descriptions, var handles, and method handles. And we're going to use that in the presentation in a while. So using FFM bindings, great. Look into the native libraries. But most of the time, we're also in a hurry, and these native libraries are already on our machines, right? So how about automating, generating these FFM bindings? And in order to make this possible, this kind of automation of generating FFM bindings, we can use a tool called jextract. Now, jextract is not a tool that's shipped with OpenGL. It's additionally created and available for download. It's a binary as well. So let's see it a little bit in action and how this one helps us to interact with the APIs. Just go here. First of all, if you would like to use jextract, if you have SDK-man, you can install it with SDK-man. Can you please raise your hand if you have SDK-man on your machine? So you can install it with SDK-man without any issues. Or if you want, you can also download the binary from jdk.java.net/jextract and run it on your machine. It works perfectly. And by the way, do not be scared that it says build 22. It doesn't mean that it works until Java 22. It means that you can just download the binary. It works with Java 24 as well. So I'm going to use today Java 24. So this lovely tool that makes some magic, let's see it, what it does. So I have a couple of projects on my local that we're going to test jextract with. First thing, this laptop comes with a native C library. So I'm going to use jextract for interacting with my native C library of my laptop, because why not? We can. Let's make this bigger. First of all, where's my C library, right? We need to find out where that is. Why do I need to know about it? Well, because jextract is going to generate those bindings to the native linker of my C library, but it will also need to know where the header files, the C header files of my libraries are. So based on that, it will generate the Java FFM bindings. So I have a small variable called C include path. And I just want to make sure that I said it for the presentation. Okay, so I pretty much said it. So this is pretty much where my C path is on my Mac. And to move forward and to generate some FFM bindings and Java bindings for my code, step, we're going to use jextract. So jextract, I need to provide an output for my Java bindings. And I'm going to say source, because that's the source. But I also need a nice way to package to, say, hey, those bindings, I want you to put them in a package. And for that, jextract uses something called a starget or -key option. So I'm going to say org Unix for my keys. And then just going to enter this one. And now I have to provide the header files, right? So to do that, I just provide the option -I, capital I, and I'm going to use the C include path that I had above to just specify to it, hey, you should use this for generating some Java bindings for the C path. But not only this, this is where my jextract is looking for the header files, but I also need to give the exact header file that I need. And for my example, I will want to use the time functions from C. So I will just go with C include path. Time.h. So let's run it. No issue. And that's again source. It generated a bunch of suspectfully Java files. So a entry point for me to connect to the C library with these all generated bindings will be a class called time_h. The name of the generated class, the main generated class, can be overwritten when you run jextract with the -header class name, -header class name option. But because in my case, I didn't do that, the default name is going to be time and the dot is transformed into an underscore in Java. And we'll see down the way how it generated a little bit of other transformations. So let me go to the time translator and do some time translation. Well, I'm working with FFM API, and generally with FFM API, I need to access native memory. And for that native memory in Java, I use the concept of memory segment. but I need a way to manage the life cycle of those memory segments that I'm allocating through Java objects. And in order to do that, I am using an object called arena. What arenas do, they provide boundaries for all these native segments that I am going to use in my Java code, but also some arenas can tell which thread is owning those native segments, but also, or how garbage collector can act on these Java objects that interact with native memory. So in my case, I'm going to use arena of confined because I will have a deterministic lifetime for my simple examples. And furthermore, so I'm going to use time. So first of all, I need to say what is the time now, but express it so that C understands it. So I'm going to say memory segment, let's say now, and I can say, hey, arena, allocate from. And with time, of course, I'm using something system current millis. I'm just, slashing this to 1,000 to express my current time as a long. And because this is a long, but this has to be also further sent to C code, I'm going to use the generated bindings that have for me a constant that it's called C_long. So what jextract does, it also generates the so-called, let's say, Java structures based on the C structures that I had in my header files in C. Pretty cool. Okay, so now I know that the time is now, but I also need another memory segment where I need to deposit my result for investigating time, right? So I'm going to call this one time. And in this one, I'm going to work directly with my generated bindings, which have a class called TM, the acronym from C. And I'm going to say allocate my entire arena for working with time using the generated bindings. Okay? Then I just go directly with another generated function called local time_r, which in C pretty much looks at the now moment and calculates the time that is at that moment and puts it usually in a pointer, but in our case, it's going to be our time variable, the previously worked memory segment. So now that we have all this, let's express a bit our time. And just make it a bit bigger. So you can see that while I was typing all this, I used all the time the generated bindings in my IDE, the Java generated bindings for my C API. And let's calculate the time. So the time has time, and I can say, hey, tell me the hour for this variable here, which is time, and then tell me the minutes, again, for time. Because I'm using a preview feature, you can see that I have a class name here, time translator, but no class name given, so implicitly declared classes. This is still a preview feature in Java 24, just let me make sure that's 24 here. And say Java -- enable preview, and then run source time translator .java. So you can see a bunch of warnings, and it says that's 309. And some of you are going to say, hey, it's not 309, it's 409 in Romania, which is true, but my laptop didn't migrate to the new time zone. It still is the one from the Netherlands. So it pretty much correctly invoked the time that is on my machine through the C library that is running on my laptop. That's pretty much like using the basics when it comes to jextract, using C, using the native linker to this library that's on your laptop. So most I think C is coming on all operating systems, and you can try it with others as well. And you can see that there's a bunch of warnings, and when I run jextract, those warnings are given to me to know that I am actually accessing native memory, and I'm working with native memory, so I should be aware and beware that working with native memory can have some side effects, and be sure when you're using that. If I would use the -- enable native access all unnamed, those warnings would disappear. Let's try another example. How about using this with Python? Now again, Python is also on my machine. And let me see, Python I think is in library, that's a lot. Clear. Library, frameworks, Python, yes, Python framework. And I need to see what versions I have. So I hope that I have a 3.11. And because Python, well, Python, what it has some C library headers that I can access, that I can tell jextract to use in order to access the actual Python library. But I need to provide my Java application a way to access the Python library, the linker itself. So I need to find that library that I will connect to. That's what I'm looking here. So in version 3.11, I need to search for a dlib, which is going to be lib and lib. I'm looking for libpython 3.11.lib. So this is going to help me further to work with Python in my examples. Okay, I did the path because I'm going to copy paste it in a moment. So what I want to do, well, I want to generate some Java bindings to the Python library as well, ideally. And in order to do that, again, jextract. So jextract, I'm going to use the all known minus output, still in source. Put this in the package called org.python, but since earlier I was looking for the dlib, it means that I need to provide the location of my linker so that the generated bindings know where to search for my linker. So I'm going to say -l, and in this case, I'm going to path to this. Okay. I don't want to copy paste too much because then I'm going to struggle writing command. Okay. Then I need to provide a way to tell it, hey, we need also to look for the headers. So where my headers are, of course, in -e, and probably it's going to be in a similar location, but instead of lib, is going to be an include folder. And 3.11, and in this case, I think it's enough for 3.11. Okay. And of course, the actual header, the C library header that jextract can use to transform into Java bindings. And the actual C library header is going to be in B. A little bit bigger, centrally. It's going to be in include Python, and it's going to be Python. .h, look, it even tells me with red, you should take this one. So let's run it. And you can see a lot of warnings about skipping. What happens is that jextract sometimes when it runs over the C library headers, it has issues in transforming all the structures that it finds there. And the structures that it cannot find proper transformation towards Java code, what it says, it's going to skip them. Now, what you can do with these warnings later on, if you find value in these structures that couldn't be transformed, you can make your own, let's say, interface so that these structures in the end are going to be transformed as well. So there are some flaws that happen over there in transforming these, but so far I didn't have issues when generating bindings for my local Python library. Okay, so I generated some Python binding, some Java bindings to my Python. Let's check it out. Okay, it's all here. Obviously, like before, it's probably going to have something like Python _h is my main Java class that I'm going to look into. Now let's invoke some Python. Now, I have a small Java class that what it does, it gets a script, a Python script that generates Duke. And I want to be able to run this one from Java. Now, some of you can say like, hey, but you could use process builder. Yeah, I could, but that's an extra headache. And this one, why not just make use of what I have locally and just put it to run for me? So how can I run Python with what I generate? And I'm just going to quickly go through that. It's a presentation for ran over me. So first of all, with the generated bindings, you need to initialize Python, and you can do that by initialize. So that's one first thing. And let me import everything. Now, one thing that you need to know when working with generated bindings, you need two things. You need all the constants, which are usually in Python _h, and you need to work with method handles, which are normally in Python, and I'm just going to have it all included. We're not going to worry about this one. So, import static, sorry, forgot something. I knew it, because PyInitialize, it's statically imported. So, PyInitialize. Again, I need an arena to work with my memory segments. So, arena of confined, again, bounded arena, and having the owner thread currently owning this arena. Okay, so what do I need? Well, I need to allocate this script and give it some memory, some native memory. So first of all, I'm going to go and say memory segment string and say arena.allocate from the script. So I can use this here. And next, what I need to do is actually say, hey, I want to run my script. And to run my Python script, I need something called pyrun. I need to think how this was simple string flags, I think. And I can use my memory segment, and because I don't need to store the result of running this memory segment, I don't need it back, I can use a memory segment.null. So I'm not interested in the result of running this native function. And last but not least, py_finalize, because I want to be done with this one. And the reason why I'm always doing the try here is because I want to, for my arena to be auto-closed when I'm done working it. I don't want to just manage the closing of my arena and the garbage collection and everything else manually. I just want to let the try statement to take care of it for me. So let's run and see if it does anything. So this should produce an image of Duke on my local, which I currently don't have. So Java, again running an implicitly declared class, -- enable preview for that. Let's run it source on Duke maker.java. Takes a little while to generate the image, but I got it here. So I got generated a Duke maker from Py through the Python script from my Java file using my generated bindings. Yeah, that works. That works with Python, but how about making something much more, let's say, impressive? Let's use OpenGL and let's use some graphics to use jextract further. Now again, the operating system comes also with frameworks for working with Qt and OpenGL. And in Mac, it's in a very interesting location. It's not in library, it's in system, library, frameworks, not too many. Say open, yeah, OpenGL.framework. And I think it's OpenGL, yeah. Let me make sure that Qt is in the same location because I need this for I need the library. So I will need to provide again to jextract the location of the linkers. This is what I'm searching right now. The locations of the linker for OpenGL and Qt, so I can tell that from generating my bindings. Frameworks, Qt, framework, yes. Qt, yeah. So they're there, good. If they're there, let's use jextract for it. Again, output. But these are two big frameworks, and maybe I don't need to generate everything for it. And a lot of people are saying, hey, you generate everything for big frameworks that are on your computer, but in the end, you don't need everything that is being generated, which is true. I just use a few methods. So let's see how we can trim that. So I'm just going to say like always source. I'm going to say org OpenGL for my target. Oh, no, not good command. Forgot the -t. Okay. Then I need to say the library location, -l. And of course, it's going to be in OpenGL. And then for each of the libraries, you need to do a -l and the 2 dots for specifying each of those. We need both of them. Now, in this case, I don't need to specify the location of the header files to be inspected based on that linker. But before generating any bindings, I want to dump the included methods and variables with the -- dump includes, and say in a file called glut.symbols, so I can trim of them. And then I just need to actually say where the glut header is. Now again, because Mac is special, the glut header is not where one's expected to be. Well, it's not maintained, so OpenGL and glut are not 100% supported anymore on Mac. So in order to still have access to them, I have used Xcode. So they are in applications, Xcode Hub app, bear with me, contents, I think it's called developer, platforms, Mac OS 6 platform, which one is this? Developer, obviously, SDKs, amazing, Mac OS 6, .sdk, system. Yeah, it's very fun to discover where they are. Imagine my joy to like search for the glut.h frameworks. No, not this one. Frameworks. No, I want glut. Maybe you have glut. Yes, you have glut. Glut and headers. Glut.h. Yes, all this lovely line for just getting access to glut.h. I use search first time that I was trying to search for it. Okay, so let's dump the includes. Oh, there's an error. So this error is being given because sometimes when I'm running jextract with some proprietary frameworks that are on my Mac, the headers are not pretty well interpreted, and when I'm compiling this, I should give it some flags in order to find my OpenGL. And to fix this, it's only specific to Mac. It's a special feature. Just going to use the compile flags. And by the way, my colleagues are working to include this in jextract, so we don't have to do this in the future. I create a file called -compileflags.txt, where I add a file called -f, and I think I'm copying, yes, this. There, should do this. Let me run this again. Yes, so now there was some generation of some sort happening. But not like in the other cases, I don't have yet some Java bindings generated here. Why? Because I said to jextract, hey, I want to check what you're generating and what you're including before actually generating code. So what jextract would do in case of glut and OpenGL, it will generate and include around 4,000 structures and methods, which is quite a lot. So whenever you're working with big frameworks and you want to generate bindings to those, you can select which constants, which methods you want to include in the generated output. And if you want to trim a lot, you can do this dump includes into a file, and then select for how many of those you want to actually include in your constants. So you're just going to delete. And don't worry about deleting something that is extra. Jextract is going to tell you, like, if it's missing something, it's going to tell you, hey, I'm missing something, you can add them back. And how do we use this dump includes moving forward? So going back to our previous command, I can use, yes, I can generate now my files by using this as an argument file. So this is a small hack that works with the JDK tools in general by providing argument files with like many commands. In this case would be like 3,800 options for a Java command or a jextract command. Now, writing 3,000 options in command line is not very practical, but what you can do, you can create this file, this helper file, and just reference it with the notation. So now I can tell, hey, jextract, generate for me some bindings to OpenGL include for my local, but only generate those bindings that are specified in the file include.symbols by using this include.symbols. And of course, use as main entry point the header file called include.h. So now let's run this. Now we run it, it takes a little. Now I have the code with OpenGL bindings generated there. Okay, let's use it. So I have some code. By the way, everything will be given at the end, don't worry, it's not magic. I have some C code that creates a T-bot. So this is the C variant. We use include to create the T-bot. And I also have a Java variant of the T-bot that will pretty much have the same code. And I'm going to tell you the differences in a sec. So first of all, I need to import statically my org.opengl.glue.h.star. And then, let me make this bigger, import the org.opengl so that I don't have any issues with my imports in my files. And let's compare the C versus Java. Now I'm going to put this to right for the Java, for the C version, and that's one for Java. And make this big and see what's going on. So in C, in order to write my code, I'll probably have an init method that I'm going to call it from a main. However, in Java, I don't need inits, but I have constructors. So what I did, I pretty much kept the same thing in init, but just made it a constructor. In here, I have constants. Well, in my generated Java bindings, the same constants have been now made available through methods. So here's the import static that worked there. The display method is pretty much the same, so I didn't have to rework a lot of code. Now, the important thing starts with the main. Because again, I'm working with a native library, I need an arena, so that I make sure that I am containing in some boundaries my access to native code. An arena I've confined. And what I need, instead of like giving, I need to allocate, like in this here was the size of the argument, argc, well, it's an int. So what I do, I allocate it from my arena and say, hey, allocate this as an int and give the value of 0. I'm not interested to initialize this with more. Then for glute init, I'm going to just keep it normal. And I'm not interested in my second variable, which was in this case a pointer. I can keep it to null. I'm not interested in binding variables, but if I make this resizable or provide the size through the arguments, I would need to init it and provide it here, not use the memory segment null. And furthermore, just glute create window to create my, to allocate to invoke from the arena, and just instantiate the T-bot through the constructor. Nothing fancy. The rest is pretty much the same, so not many differences. Now let's run it. In this case, I have a proper class name, so no more enable preview for running it's not an implicit class, just a declared class. So let's say Java source tpot.java. Okay, so there's an issue. What happens is that, it's not instantiated by the main thread. So to fix this situation, and whenever you see this kind of error, working with glute, you need an extra flag to stale to the JVM, which is called the start on first thread. And what the start on first thread is doing is used to ensure that the Java application is starting on the first flag that on the first thread that is available for a GUI event, because this is going to be a GUI event. So Java -x start on first thread. And I also want to debug, because when I'm interacting with native memory, I want to know what parameters I'm sending to that native memory. Right now, I'm just, calling a lot of bindings that I hope they do something to my native library and they produce something nice, right? So in order to do that, jextract has a parameter called jextract.trace downcalls. Downcalls is true. And now source teapot.char. Okay, nice teapot. So this is my teapot here. In the example that's available in the extract samples, this one rotates as well. My example is a little bit lazy, it doesn't have the idle function that rotates the teapot. But I put it a cooler color than they have, and my colleagues have done for the original example, so that's it. Now, let's look at the output here. Because I gave the trace to my down calls, I can see how the parameters are being passed to my native memory, but also what address in the memory I am using and what's the size of that, right? For each of the parameters that my code is using. So whenever I'm using a memory, I can check the address of that there. So this is pretty useful trying to debug and write and understand, like, where's my code going through when running from Java further. Now that this is done, let me close my debug. This is great, right? Interacting with native libraries, and pretty much everything works streamlined. There were some issues, but yeah, I managed to fix them. However, there are libraries with which jextract doesn't work by default. So because they don't provide a library header, meaning a .h file. What do we do in these cases? Well, in these cases, we kind of need to generate those C library headers. So it's the case of Rust. Rust is a great programming language, but it doesn't come on our computers with a default C library header that we can access through. So for our example, I have a hello world in Rust, where I used cbindgen, like one of my colleagues has detailed, Jorn Vernay. And what I did in that case, I have this lib.rs where I have a small hello world that helps me to expose as a C library a simple hello world function written in Rust, but for me to invoke it through Java. So this is just a simple example. As I said, I need a linker, right? And I need to link to it. And my linker, the library to which I will link, it's this librust_panama_hello world.dlib. So like in the case of Python, I will need to look for the dlib that I'm generating thanks to cbindgen. And of course, I will need the library header, which is lib.h here, pretty much a standard C library header. So let's write some jextract for this custom-made Rust library, well, C library based on Rust. So let's say jextract, like always, output and source, target org.rust, and in this case, include the function that's called hello_world. Then again, I need to put the linker, and my linker is in here, so I need to copy the path and the reference to this one off the root here. Paste. Then I also need to give where my header file is. It's here. I'm just gonna off reference. Yes. So now I can have this generated for Rust as well. Now this is not going to be very impressive because, well, it just prints hello world. But just for the sake of it, let's run another implicitly declared class and just say hello world. And here, import static from Rust. And of course, it's implicitly declared --enable preview and source simple rust.java. Oh, somebody didn't paste correctly. Oh yes, I think I know what I did. for the linker. Yes, I always have an issue in forgetting this 2 dots. And of course, I couldn't find linker, hence my issue in running my simple Rust. So yeah, pretty much not impressively printed hello world, but this is just a simple example for you to see how it works with Rust. Now that examples are being over, and running a bit over anyway, I don't want to keep you a lot from a break. Now, what all these examples show is that we have another way to substrate native access in the JVM. And this is just the beginning. Jextract samples actually feature, I think, 20 examples of interaction with native libraries. And I would advise you to look into all of those and look into building your own. People have had a lot of fun in using foreign function and memory API to interact with native libraries and even further. So much fun that it got even adopted already in products that maybe you already use. So for example, products like Netty, Lucene, Apache Tomcat, VM, and more are already using what you saw today at a small scale, meaning the FFM API. And sometimes these libraries or others that are being in the build are using jextract to generate their Java bindings because you don't want to spend all the time coding everything from scratch when you can use a tool that generates things for you. So this is a bit over time, but something I had to say. If you want to try FFM API, this is available with JDK 24. If you want to check which cool projects are being done with FFM API, most of the time, Panama Dev gets a lot of information about new tool projects that use FFM API. You can use jextract and you can download it. There's a guide for it. And of course, there's samples that you can try to build on your own. And yes, as always, feedback is being welcomed, is welcomed. I enjoy Vox Days, actually the last part of it in the last panel. This is where you find all the slides with all the links, and just see you around in the break. Thank you. And thank you for staying over.